This is section 11.3, Electronic and Molecular Geometry. Our objectives are to identify the most likely type of bonding, ionic covalent or polar covalent, draw Lewis structures for ones that violate the octet rule. From a list of binary compounds, identify those that require electron promotion, talk about that, and then talk about hybridization and why it's necessary. Alright, first of all, let's talk about electronegativity, and this is a chart off ptable.com, and if you can't read it, you can always go to ptable.com and look at electronegativity, and you'll see that if you look down here, these are numbers that are electronegativity numbers. This is based on the Pauling electronegativity scale, and this allows us to figure out compare the differences between these electronegativities to decide if things are ionic, covalent, and so on. And so the way that we do this, if we look at these, and we talked about how, hey, you can look at metal, non-metal, and that's a pretty good rule. This is just a little bit tighter on that, a little bit better. Some things form covalent bonds and they're pretty close to the same thing. Maybe they're exactly the same and they'd be zero, or they're really close. And I've always been told that like 0.4 or less is usually considered to be a non-polar bond. So when the difference between those two numbers that we were looking at on the last chart is less than 0.4, that's considered to be non-polar. If the difference is somewhere between 0.4 and 1.7, we consider that to be polar covalent. It's a covalent bond, but yet it's going to have a charge. And the reason is, let's say you have something like hydrogen and chlorine is very electronegative, so it's going to keep that electron just a little bit more. So it's going to keep that, it's going to have a little bit more of a negative charge. Hydrogen is going to have just a little bit more of a positive charge when it's all said and done. Now, the way that we usually indicate that is we write this little symbol like this, kind of looks like a funny looking S, and put S minus. So it's not a full like ionic charge, not the same thing like it lost an entire electron, but it does have a noticeable effect, and you can actually test that. And then this side would be a little bit on the positive side. So what we're saying is that chlorine just keeps the electron a little bit longer. If it's greater than 1.7, anything greater than that, we would consider it to be an ionic bond. It's going to completely give up an electron. Okay, so let's talk about some of these things, and we'll talk about electron promotion. Let's say we have this molecule, BeH2, and this is actually a covalent. Even though beryllium technically is a metal, the difference between beryllium and hydrogen is not 1.7. So this is a molecular compound. And if you notice that beryllium would be 1s2, 2s2, and to share, we're going to have half-filled sublevels. We're not going to share if we've got a full sublevel. So why would beryllium want to share? Well, it does though. And so what happens is it actually promotes this electron up into the p sublevel. So, what happens is you've got, like, this would be what it normally is, 1s2, 2s2, but this electron is removed from there and promoted up into there. So now we've got 1, 2 half-filled sublevels to create those bonds. So it can create two bonds. And this really no longer just an S sublevel overlapping like we talked about the bonds that happen when it happens, or P sublevel. It's more of a combination between those two. They're no longer S's and P's. And it's what we call hybridization. And this would be known as an SP. And the reason is because you've got an S and you've got a P, and so S and P combination, a hybrid, and that's your sp hybridized bond or orbital that you have there. There's all kinds of different hybridizations, and we just simply name them by how many, does it involve S, does it involve P's, does it involve D's, what do we got? So let's take a look at, if you're in group 3A, your original thing is going to look like this. You're going to have 2 in the S level and 1 in the P level. But one of those S level ones gets promoted. So now you've got 2 in the P, 1 in the S. You've got 3 half-filled sublevels, orbitals rather, and so you can now form 3 bonds. And this becomes what is a hybridized bond. It is an sp hybridization bond. sp2 hybridization bond, because you've got 2p sublevels there, or orbitals. And here's a couple examples. Boron can do this. Forms BH3 and BCl3. Those are all hybridized bonds. Each one of these would be known as an sp2 bond. So if on the test it said, hey, what kind of bond is that? You would say, oh, that's an sp2 bond because it had to be hybridized to get to that. But also notice that these are exceptions to the octet rule. Notice that boron here is missing, there's no electrons there, so it only has 2, 4, 6, it can only count 6. So it's an exception to the octet rule, and these happen. I mean, it's still more stable, it's not as good as 8, but boron cannot get to 8 because it only starts with 3, no way for it to do that. Alright, let's take a look at group 7A, or 4A rather, group 4A, and typically they're going to be S2, S2P2, so 2 in the S, 2 in the P. Carbon and silicon are examples of that. And so we've got our S2P. And we can promote one of those S electrons, and now look at, we can form 4. We have 4 half-full orbitals, and so now we can form 4 bonds. And this is known as sp3 hybridization because, why? Because we've got an S and we had 1, 2, 3 P's, and we put that together, so we call it sp3. So that's all you got to do is figure out, well, which one, what do we got? What are our bonds? This, once again, these are all, you can no longer tell if it's an S or a P. They're all the same. That's all a combination. It's somewhere between what an S bond would give you and a P bonds would give you. It's an sp3 bond. Let's take a look at group 5. Nitrogen and phosphorus would be examples in there. Nitrogen can only form 3 bonds. Notice that it's got 3 half empty ones here, and there's no, you're not going to promote one up there, and you're not going to gain anything by doing that. So it's only going to form 3. So it tends to form compounds like CCl3 or something like that. P, phosphorus, on the other hand, can actually at times form 5 bonds. So take a look at why this happens now. This is phosphorus, and it's just 2 in the S, 3 in the P, but there's an available now 3D level. And there wasn't an available level for nitrogen. There's no 2D. So what it can do is promote this electron up to here, and now you have 5 empty or half empty orbitals. So you get something that looks like this, and now you've got 1, 2, 3, 4, 5 possibilities. This is known as the hybrid sp3d. Why? Because, well, we included an S, we included 3 P's, and we included 1 D. So sp3d hybrid. Let's take a look at group 6. Okay, they would have 2 in the S, 4 in the P. Sulfur and above, because they're big enough, have an available D sublevel. So oxygen wouldn't be able to do this. Sulfur can promote this electron, can promote that electron, can move them up to here. So you get something like this. So notice you've got an S, you've got 3 P's, you've got 2 D's. So what do you suppose this particular hybrid is called? Hopefully that's what you said, sp3d2. And there is an actual compound of sulfur where it forms 6 bonds. Once again, if you look at that, it's going to be sulfur with 6 fluorines. And obviously that's an exception to the octet rule. All the fluorines would be happy, but sulfur would have count 12, if you counted those bonds. So it's another exception to the octet rule, which is not, the problem is the octet rule is a good base, but it's not perfect. I mean, and there's a lot of different exceptions to that. Let's look at group 7. Those are S2P5. Most of the time, they're going to form one bond. There's things like chlorine and fluorine and bromine. Occasionally, if you got big enough ones, if you got chlorine, chlorine can promote one of its p electrons to the d. Therefore, it can form 3 bonds. It's got 3. It would have 3 half-filled. Can also promote at times 2 electrons, and then it could have 5. Could form 5 bonds. But once again, smaller things, fluorine is not able to do that because it does not have an available D sublevel in order to promote the electrons to. Even, it's even possible for some of the noble gases to do this. Not a lot, and they don't like to do it. I mean, it takes, it's usually extreme conditions for it to happen, but it's possible. Xenon is probably the most common one. You can promote 1 electron, and if you promote 1 electron, you create 2 empty shells, or half-empty sublevels, and so it can go XeF2. You can even promote 2 electrons, have 4 half-full sublevels, orbitals, and then you can get XeF4. And there you have it. That is the end.